So, good morning. Thank you for the opportunity to be here with you. I come from Britain, so my accent is probably a little bit unfamiliar, but I am speaking what I think is English. I'm going to be talking to you this morning about pulsars, pulsating radio stars, and I want you first to imagine you've got about 2,000 satellite TV antennae. You connect them up together with some low-loss cable. You plug them into a really, really good receiver, point them at a carefully chosen bit of sky, and if the technology works, you hear this. Sounds like a truck or a tractor, one in need of some attention, but it's actually a star. That's 10 to the power 27 tons of stuff, all spinning 11 times a second. 11 times a second is 660 RPM. The internal combustion engine idles about 700, so that's why it sounds a bit like a truck, a tractor. It's a pulsating radio star, otherwise known as a pulsar. I'll say just a little bit about where pulsars come in the scheme of things in astronomy. So I'm going to give you an overview of the birth, life and death of stars in about 5 minutes. This is very overview. The Sun is a typical star and has a life of about 10 billion years. So it's short, this overview. The first slide is part of the sky that you can see in wintertime, constellation of Orion. Perhaps the most notable bit is Orion's belt, the 3 stars in a line. The bright star here is the left-hand star of the belt. And what the slide is showing you is a nearby nebula known as the Horsehead Nebula because of this shape. Looks like a horse's head. It is actually some of the dark material from below it standing up and being silhouetted. And it's silhouetted against some hydrogen. Hydrogen glowing in its red spectral line. There's a lot of hydrogen in the universe, so when you see an astronomical photograph with some red or pink stuff, you can say, ah, hydrogen. And you'll be right 95% of the time. So that's some hydrogen. Those of you near the front can probably see that there's a lot of stars in the upper part of the slide, relatively few down below. That's because the Horsehead and the cloud it comes out of is a dark cloud that's opaque, does not transmit light. It's a bit like having a curtain or a drape drawn across the sky. You can see the relatively few stars this side of the curtain, but you don't see any beyond it. And it's in dark clouds like this and dark lanes like that that stars form. When perhaps because a shock wave goes through, perhaps by chance, particles of gas and dust that make up this dark cloud congregate. Initially it's a very small congregation, but it's got slightly enhanced gravity, pulls in some more particles, puts up the mass, puts up the gravity, pulls in some more particles, puts up the mass, puts up the gravity. And what started as a fairly small knot, over a period of 1 million or 10 million years, grows and grows and grows. And the temperature in the middle rises because of the pressure of the overlying material. And when the temperature reaches about 10 million Kelvin, the nuclear fusion reactions start, hydrogen is converted to helium, and the star shines. This photograph is of a group of stars close to Orion, known as the Pleiades, or the Seven Sisters. You can see them with the naked eye, and it's quite a good test of your eyesight. Just go out somewhere dark, give your eyes 10 or 15 minutes to properly dark adapt, and then see how many stars you can see in this group. You find the route by tracking up Orion's belt to the right, and just keep going till you come to this fuzzy patch. With a big telescope, it looks like this. These are actually very young stars. They're very luminous, they're very massive. Because they're massive, the central temperature is that little bit higher, and the reaction rate is very, very sensitive to temperature. Temperature to the power 17 at the smallest. So a very small increase in mass puts up the temperature, puts up the reaction rate hugely, and it produces a lot more light. So they're very luminous. They won't actually last very long. They're really rushing through their resources. This is southern hemisphere. You won't be able to see it from here. It's called the Jewel Box, and so named by John Herschel, who was studying at the Cape in South Africa. And he called it the Jewel Box because a number of stars in this group show colours. And the one that you can see best is that one, which has an orange tint. People near the front may be able to see pinkish tints around some of the other stars. You shouldn't be able to do so. And it's not a reflection on anything you did last night. It's not your eyesight. To make this kind of photograph, you take 3 monochromatic photos through green, blue, and red filters. And then you put the 3 photographs together to make a colour picture. Whoever put the 3 together was a bit heavy with the red, so some of these come out rather redder than they should be. But that orange one is definitely orange. And that's a star towards the end of its life. It has exhausted the hydrogen in its core. The core is clogged with helium, and in fact there's another nuclear fusion reaction converting 3 heliums to carbon going on in the core of that star. And toward the end of its life, our sun will go red like that and will swell about 100-fold. The Earth is about 100 solar radii from the sun, so when it swells 100-fold, we're in trouble. We may or may not quite be engulfed by this sun in its red giant face, but either way, the Earth will be a cinder, and we won't be staying here. But in the sun's case, that's not due for about another 5 billion years. After that swelling stage, the sun and many other stars shed their outermost layer. And you can tell what the outermost layer is made of. Young pink stuff, hydrogen. That star in the centre is the remains of the star. This is actually a shell of material, and that star has nothing to do with the story. It just happens to be in the same direction. This is an extremely thin shell of material, so it looks like a ring. Can you envisage a kid's balloon blown up really big, and you trying to decide what colour it is? If you look at it face on, it looks kind of whitish, but if you look around the rim, you see the colour rather better, because you're looking through a greater thickness of material when you look at the rim. Similarly with this, you've got a greater thickness around the rim, but it is actually a 3-dimensional shell. The Pleiades, the Seven Sisters again, not only are young stars, but are going to die young, because they are consuming their resources at such a rate. They're the astrophysical equivalent of the young man in a sports car. Very bright, very flashy, but it doesn't last and there's no money in the bank. These stars are going to die young, but they're important for the pulsar story. They managed to have a whole sequence of nuclear reactions in their cores. Start the same way: hydrogen converts to helium, helium converts to carbon, and they can convert carbon to nitrogen, oxygen, on up the periodic table, silicon, sulfur, till they get to iron and nickel. And iron, you may remember, is the pits. You can fuse light elements and get energy out. You can fission heavy nuclei and get energy out. With iron, you cannot get energy out. And when these stars get an iron core, it's the end of the road for them, and they do something quite dramatic. This is another southern hemisphere photograph. Large Magellanic Cloud, a small nearby galaxy. Lots and lots and lots of stars, more of this here pink stuff, of course, it's everywhere. And top left, a mass of glowing gas and probably stars. Do you see on the bottom right, one star is being picked out with an arrow? Just to be absolutely clear, for those of you who don't know astrophysics, the arrow was added afterwards. But watch that corner of the photograph. That inconspicuous star that we had to identify with an arrow has exploded, and exploded catastrophically. It was one of these big stars. This is the kind of thing the Pleiades will do 100 million years hence. It was one of those big stars, massive stars, 10, 20, 30 times the mass of the Sun, has run right through its cycle, ended up with iron in its core, tried to get energy out of the core core's collapsed, the material outside comes rushing down, hits this collapsed core, which is like a brick wall, and bounces off, and there's an explosion. The core of the star is what becomes one of these pulsars, or pulsating radio stars. And they're also known as neutron stars because they're rich in neutrons, and I tell you that now because I sometimes switch between the two without realizing. So pulsar, neutron star, they're the same thing for the purposes of this talk. This is the remains of a star that exploded about 1,000 years ago. There is one of these pulsating stars in the center. It's a rather spectacular nebula, and it's kept energized by that pulsar or neutron star at its core. And this is the remains of a star that exploded about 10,000 years ago. The explosion was actually somewhere way off to the left, or on this slide, explosion maybe somewhere about here. And in the 10,000 years, the material has gone out to here. This is the front, where the material expanding has got to. And this material is enriched in useful chemical elements like iron and calcium and carbon and oxygen, and it is the source or potential source of those chemical elements for living things. Also in the photograph, well, there's some pink stuff, and there's lots and lots of faint stars, and those of you near the front may be able to see a track running across from top left to bottom right. To take the photograph, the shutter on the camera was open about 20 minutes, and during that 20 minutes something went zoop across the field of view and also got captured in the photograph. It's probably a piece of space junk, ex-satellite. There's rather a lot of debris up there now. It's quite hazardous for astronauts and to some extent for satellites as well. And there's rather more at the moment because in the recent past, two nations, in order to show how clever they were, each zapped one of their own satellites into millions of bits. Most of the bits burn up in the Earth's atmosphere, but occasionally a lump lands and disrupts the air schedule. It's most wonderful when it does. So the pulsars, the neutron stars, they're the cores of massive stars post the explosion that we always thought ended the life of those stars. And their properties. I've already mentioned 10 to the power 27 tons, a mass like the Sun. A radius of 10 kilometers. And I don't mean 10 to the power something kilometers, I mean 10 kilometers. So you could put one down on Vancouver, and Vancouver Island would be perfectly okay. If you put that amount of material in that small a ball, you get some spectacular densities. Average density is like the density of the nucleus of the atom, which is one of the densest things we know. I find that quite hard to envisage, so I have this analogy which maybe helps a bit. You take a sewing thimble, preferably a nice silver one. You take the population of the world, 7 billion people, and you jam the people one by one into the thimble. When you've got all 7 billion in the thimble, it weighs the same as if it was made of neutron star stuff, pulsar stuff, or for that matter, the nucleus of the atom. It's very, very dense. Such density produces some very interesting physics. The gravitational force at the surface is spectacularly strong. So if there were a quote, mountain 1 micron high on the surface of one of these stars, the work you do climbing up that micron against the local gravity is like the work you do climbing Everest here on Earth. And the atmosphere is correspondingly pulled down. If you're considering just gravity, the atmosphere is just 1 or 2 centimeters thick. So if I'm standing on a neutron star, the atmosphere is slopping around between my toes, and I have to get my nostrils down at toe level to breathe. I think we'd be a different shape if we lived on a neutron star. You probably also know that gravity bends light. The light round a neutron star, the light on a neutron star, is bent something like 20, 30 degrees. So I can stand on one part of a neutron star and look around, and I can see 2/3 or 3/4 of the surface, just by standing in the one spot. It must feel very peculiar. Gravity also redshifts light. So if there were little green men on one of these stars, they'd look to us like little red men. And gravity also affects clocks. We've probably already been told about how GPS and sat-nav makes corrections for the different clock rates up at the satellite and down here on the Earth. It's even more extreme with one of these stars. So supposing I take a great big clock and go to one of these stars, you stay safely on Earth, but with a very big telescope, so as you can read that clock, you'll find that when I'm on the surface of this pulsar neutron star, my clock is doing 1 tick every 2 seconds. I can take my pulse with my big clock, seems okay. It's the additional gravitational force there is slowing the clock and slowing my heart similarly and slowing my metabolism. The gravitational effects are quite remarkable. There's also a gradient of gravity. Suppose I'm coming into land on one of these stars, and I'm coming in feet first, because that's the ladylike way, to land on a neutron star. And as I'm coming in, the gravity's pulling me down hard. But the gravity changes quite markedly with height. So the gravitational force on my feet is much bigger than the gravitational force on my head. And my body gets stretched. The technical term is spaghettification. But the difference in force between my feet and my head is so big that the spaghetti breaks. Your body is torn apart. And even if I curl up in a ball, the difference in gravity between the lower part of my body and the upper part of my body is sufficiently strong. You're torn apart. So don't go visit a neutron star or a pulsar. There's a phenomenal magnetic field. We think they're somewhere around 10 to the 8 Tesla. To put that in context, your fridge magnet is about 10 to the -2 of a Tesla. And a laboratory magnet that somebody's terribly proud of reaches about 10 Tesla. This is bigger than the biggest magnetic field we can make and sustain. And we really don't know how the neutron star makes it, which is a bit galling.